Hi, can you hear me?
Yes, sir.
Okay. Okay, I think we can start. So I think this time we can complete topic of coaxial circles. We have to solve a few problems now. Okay, are you able to see the problem sheet?
Yes, sir.
Yes, sir.
So last time we completed question one and two. So if you have spent some time at home, you might have solved question three, four, and five also. So can you raise your hand if you have solved question three or four? Okay, four or five people have done it. So, I mean, for those who have solved those questions, you can proceed to the next questions. And for others, I'll just give you little time, not much, maybe 5 minutes to try question three, and same for question four. Okay, so question 3. What you are given is a circle with diameter AB. And a point P somewhere. Okay, and the question is the circumcircle of PCD is orthogonal to the given circle. This is what you have to do. So, can you recognize that this diagram is a subset of something that you already know? Have you seen this diagram somewhere before? What are these points C and D?
Feet of altitude.
Feet of altitudes, okay. Yes. So those are the feet of altitudes. You can relate this diagram to a standard triangle ABC with the orthocenter configuration. Okay. So in a standard triangle ABC, if you construct the altitudes, basically what the two circles we have to consider. So the gamma is one circle, and the other circle we want to consider is circle with passing through PC and D. Right. So what are these two circles in our standard diagram? That is what we have to first locate. Okay. So I won't call them ABC because it will confuse us. But we can call this ABC, this A, B, and P. Okay. So you see this, the diagram on the right and diagram on the left are the same.
Yes, sir.
Okay. So then we know some properties about the diagram on the right. So we can try to use them to prove the part on the left. So in particular, uh, so if I draw the circumcircle of PCD on the right side, okay, what is its center going to be?
Midpoint of pH, like if the intersection is at.
Yeah, that midpoint of pH. And pH is going to be the diameter of this circle. Right? Let me just draw this circle again. So the midpoint of this line PH is the center of this circle that we know. And then what is the other gamma circle that is given to us, which is that circle on the right side? So the circle with diameter AB will also pass through C and D, correct?
Yes, sir.
And what is its
Yes,
center? Its center is the midpoint of AB. So if I call it M.
Yeah.
Okay. So now coming to what we have to prove. So we want to prove that these two circles are orthogonal. Now multiple definitions that we have, but the simplest one to work with is related to the centers of the two circles and the distance between them. So if I call this center X temporarily, so I am interested in the distance xm, and if I show xm square equal to r1 square plus r2 square, where r1 r2 are the radii of these two circles. So let's say r1 is the radius of this small red circle, and r2 is the radius of this bigger circle. So if I show this, I am done. Okay. So this is where what we have studied before related to orthogonal configuration, 9-point circle, all of them will be relevant. So what are point X and M related with respect to the 9-point circle?
They are diametrically opposite.
Opposite. Firstly, 9-point circle, but not only that. So XM is the diameter of the 9-point circle. So and do we know what is the size of the 9-point circle? So the main triangle APB, okay, if we call it circumradius as R, then what will be the diameter or rather the radius of the 9-point circle?
R by 2.
Is R by 2. And if XM is the diameter, so what will XM be equal to? XM is also R, right? Okay. So XM is R that we have figured out. So now the RHS, R1 square plus R2 square. So if we know the radii R1 and R2, then we are done. So R2, what is the radius of the bigger circle with diameter AB? R2 is simply going to be AB by 2, right?
Yes, sir.
Okay. And R1 in the above diagram is basically PX or XH, any of them. But particularly it is half of PH by 2. Okay. Now, is there anything else that you know about this diagram which can help us to solve this
So
problem?
PX is equal to OA dash. That is OM.
Yes. So another property that you may have studied is this OM is half of PH. Are you aware of this property?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So then are we done? Because then we have all the pieces required, right? Because basically I can apply Pythagoras theorem in this triangle. In triangle AOM, I already know that AO square, which is R square, is equal to AM square plus MO square. Okay. And out of that, so AM is exactly the radius which I want. So AM is exactly R2 and MO is equal to R1, because MO will be basically this is equal to OM. Okay. So in case you're not able to follow this, just go back and revise these concepts. I mean, all of these properties you would have studied in great detail in the 9-point circle. So just it was a matter of applying them, seeing that configuration fits here nicely, and then applying those properties. Okay. And this is something you have to do multiple times in various problems. So you have to get used to that. Okay. Do you have any alternative solution for this problem? Because I mean, we could show orthogonality in so many different ways.
Sir, I used converse of tangent secant theorem.
Okay. Sure. Can you tell me your proof? So I'll draw the original diagram again.
Sir, let O be the midpoint of AB.
Okay.
I constructed a ray OC
Okay.
and let M angle OCA equal to X.
Okay.
Now M angle OAC equal to also X,
Yes.
and M angle CDB equal to X. 180
C.
minus X. And M angle, let K be a point such that O dash C dash K.
Okay.
Now M angle KCP is also X,
KCP is X, correct?
and now M angle PDC is also X.
PDC is also X, correct?
So KO must be tangent to circumcircle of PCD by CTST.
Yes, yes, correct, correct. Yeah. Yeah, this is a very nice proof actually. So through angle chasing, what we have shown is that the circumcircle of PCD is tangent at OC, which means that, I mean, basically the center of circumcenter of PCD will form a 90-degree angle here. So basically the angle of intersection between the two curves is exactly what we have computed here, and that is equal to 90 degrees. Yeah, this is also very nice solution. Okay. So let me ask you one question. Oh, okay, okay. I was wondering where will we use the fact that AB is the diameter, but yeah, we use that because we use the point O. But let us try to think here for a minute. I also don't know if there is any possibility of generalizing this, but so this is also something we should learn. Wherever we solve problems, we should try to construct new variants of the problem. So what is you have to understand really why every property given was required. So for example, AB being the diameter, suppose you draw the same diagram without AB being the diameter. So any general diagram you draw. Okay. So AB is just any chord, not necessarily the diameter. And now I draw this configuration. I mean, what was it in the left diagram which worked, which will not work in the right diagram? So that you really need to understand. So in my previous proof, of course, the whole thing worked because DC and AD were altitudes. They are not here. But in this other proof, right, which uses angle chasing, what all can we find out?
Angle OAC and OCA are not equal. So then it
Yeah,
will-
correct. So if I consider the midpoint, right, then yeah, what you're saying is correct. So you may not get orthogonality, but I'm just trying to figure out, do we get something else or it is completely, there is no useful property? So, I mean, I could generalize this question. Here, in other words, what I was asking is find the angle of intersection between these two circles. And in the left hand side, the answer was 90 degrees. So now I'm asking the same question, find the angle of intersection between these two circles in the right diagram. And the answer may not come out 90 degrees, but whatever that answer comes up, so that is how we could generalize this problem. Okay, so let's just give this. Let's see if we can crack it in a few minutes, or else we can try to solve it later on. But this thought process is important for you to try more and more yourself. That after you solve a problem, don't just leave it and move on. See how you can generalize it, extend it, make some variations out of it, because that will really push the limits of every tool that you know. I mean, you will start to realize where every tool, up to what point that tool or technique works, and where it breaks down, where you need some different strategy or different problem solving technique. Okay. So is the problem clear for everybody? That now I want to find the angle of intersection between this red curve and the blue circle. And the angle of intersection we have defined last time. It is the angle formed by the tangents at the point of intersection. Okay, so this is how I'm starting to think of this problem. uh, I don't know if this is the best idea or not. But basically, as I said, there are too many moving pieces in the diagram. So we have to fix some objects. So we'll fix this circle with center O and points A and B. So all of this we will keep constant. So we will not try to move these things, but we will try to move the point P. Okay. So point P is the variable in this equation. So basically, you can imagine point P. You can freely choose anywhere in the whole plane, and so that will of course then C and D will also shift. Of course they will remain on the blue circle, but they may change. So P, C and D are the variables as such. Okay, but that also gives me a lot of freedom. I mean, it is very hard for me to track the problem this way. So let us constrain the problem a little bit to begin with. So I am interested in angle of intersection, right? So for that, what do I need? I need basically the two circles wherever they intersect. I want to draw the tangents at those 2 points. Okay, so what if I start by trying to keep one of even C and D constant? So let's say for now we keep point D constant. Okay, so if point D is constant, which means that P can only vary on this line. Okay, so this line BD is also fixed, so P can take various positions on this line. Okay, and as P moves on this line, of course C will also move, right? So if I take point P over here, for example, then point C will come somewhere here. Okay, so P and C will still change or in position, but point D is fixed now. And what is the advantage of that? Because now, I mean, OD is fixed, so the angle of intersection I'm interested in, out of that, one tangent is always going to be fixed. So now I only have to worry about what is the other tangent at point D. So the circumcircle of PCD, this circle will vary, but I'm interested at what is its tangent at point D. If I can see that properly, then we are done. Okay, so let us think. So at this point, it is not clear to us what that tangent, what that other tangent might be. Okay, in this diagram, it seems that, I mean, here the center of PCD is somewhere over here. So in that case, the tangent is like this, and in this other case, the point is somewhere here. So roughly speaking, from this diagram, it seems that the center is always on this one particular line, which means that this tangent will always be the same. That is what it seems, but we are not sure. So we can take some help from software like GeoGebra here. Okay, of course we don't have the freedom to do this in exam, but while studying, you can use GeoGebra sometimes. But I'll warn you that you have to also be efficient at drawing the diagrams on paper. So GeoGebra is a helpful tool to explore some ideas, but it is not a substitute for drawing on paper. Okay, but with that, let us give it a try. So let me draw a circle. Okay, labeling is a bit off from what we have, but anyway, we just draw the configuration. So I could take the point P first, and let it intersect this. But instead, I'll start with the fixed point. So the point through which I always want the PV to pass. So I will choose that first. Okay. So then basically my variable point P has to lie on this line somewhere. That is how I force the problem to be bit constrained. Okay, so this is my point P. Let me at least call this point P. So if I join this, okay. So I am interested in the circle of PEF, or rather the circumcenter. And let's see what happens. I mean, there are no guarantees. It may turn out that that locus is some very bad curve, then we have no option but to abandon this. But if it turns out to be something good, then there is a potential. We are not still proven anything, of course. In this GeoGebra, we are just trying out things. We are experimenting. We still have to come up with the proof. Okay, so now if I move point P, what happens to this point G? And obviously, as point G moves, the tangent at point E will also change. So if I just call this, so I can enable tracing for this point. Okay. And now let's see what happens when I move this point P. Look at that. It seems very much that the point G always moves on a straight line, which means that the tangent to this circle at point E, which are not drawn, okay. So the angle which you're interested in is obviously, so this is the first tangent. Okay. And this is the second tangent. So as point P moves, obviously you see that both tangents are the same, which means the angle of intersection between the two circles is also constant, which is quite amazing. And now I have another possible idea. So here we chose only the points P lying on this a particular line. So we kept the point E constant. But what happens if we move the point E itself? Oh, look at that. Even if I move the point E, do you see the angle between these two tangents is the same? Which means that the answer to this question, angle of intersection between these two circles, doesn't depend on the choice of P at all. So now let me decouple point E from this circle. I don't want point E to be on the circle anymore. Okay. So I have to redraw some part of the diagram. But I could choose the point P anyhow I want in the whole plane. Okay, so this is any. So I'm interested in the angle of intersection between these two circles. So let me just draw the construction midpoint. Okay. And now let me move point E anywhere. You see the two tangents are exactly the same angle between them. So what the question we asked was just a special case of this one. So there the CD which I'm drawn below was the diameter. Now it's no longer diameter. Now if I make it the diameter, obviously this angle will become 90 degree. The two circles will become orthogonal. Okay, so this is roughly I made it a diameter. Now you see obviously the two tangents are 90 degree to each other. So I think you can probably derive that angle based on this segment CD. So what is the angle this CD subtends at the center of this circle? So the angle COD, sorry, oh, whatever, you know, this angle COD, if I give that angle to you, you can probably determine the angle between these two tangents. Okay, so that is quite interesting that we started with one problem, but we have a completely different and probably more interesting problem. Okay, and anyway, I mean, I won't spend more time on trying this. but because by the way, very important to note that even I didn't know this idea. So this is property that only RMO batch of 2021 has discovered. Even batch of 2020 doesn't know about this property. Okay. So that is how you explore ideas. You try out something, you come up with some conjecture, you do a few experiments, maybe it works out, then you try to prove it. So now the homework for all of us is to try and do this property. And of course, then if somebody comes with even a better generalization, more welcome. Okay. But let's see. I hope that does anybody already have proof of this? Because I don't see at least.
Yes, sir.
Oh, you
Sir,
already.
we can prove that angle between the tangents is half of the angle subtended in the center.
Oh, wow. Okay. That is nice. Okay, but let me also try it and others also try it. Let us not reveal the answer for everybody. So we'll take this as a homework, okay, for everybody to try. Okay. But I hope you got the idea of how you can take a problem and generalize it to something different and try out a few ideas. Sometimes it works out, many times it doesn't work out also. I mean, there is no guarantee, but you have to give it an attempt. And there could be other properties also waiting for us to be discovered. So the more you experiment with this diagram, the more insight you might come up with. So I very much look forward to learning about new properties which you have discovered. Okay, so I'll always be happy to learn about that and share it with others. Okay, question 4. Can you raise your hand if you solved it? Okay, 1 or 2 people have solved it. Okay, I'll give you 5 minutes to try. Okay, question 4. So what all is given? The standard orthocentered circumcenter. Okay, so I want the, oh sorry, I'm not sharing my screen. How do we do this? So let L be the line passing through A and perpendicular to OX. On the line L, let L intersect BC at point R. Okay, so my claim is R is collinear with the feet of altitude. So if I call these points E and F. So first part which we are claiming is that E, F, R are collinear. Okay. So how many of you solved this part? Can you raise your hand? Nobody? Okay. Hmm. So in questions like this, one very useful idea is inverting the problem. It seems very difficult to show that this point R lies on line EF. What if I show the other way around? Let me not construct this point R at all. Okay, this way. I will instead extend line EF. Okay, this is my construction that we will extend line EF. Okay, let it meet the base at point R dash now. Okay, and if I show that R dash lies on the line L, then also I'm done, right? And
Yes, sir.
what is the same as showing that that is lies on line L, because line L is nothing but perpendicular to OX. So if I show AR dash is perpendicular to OX, is that sufficient?
Yes, sir.
Yes, sir.
Okay, so then with this, I'll give you another couple of minutes to try. You can raise your hand if you solve the part whenever you solve it. Okay, Jaideep has solved. What did we do just now? What is point X? What are point both O and X?
They are centers of circles.
The centers of circles. Which circles? I mean, if you just, even without telling which circle, think in your own mind. O and X are centers of particular circles, and we
So
are
triangle AFE and triangle ABC.
correct. Triangle AEF and triangle ABC. Everything is on the table. There is nothing that is hidden. So let me draw the circles in question. So just now in the previous part, we were talking about the circumcircle of triangle AEF. So we know that X is the center of that circle. Okay. And consider another circle, which is the circumcircle of ABC itself. Okay. Okay. Not drawn very nicely, but okay. We have a- Oh, it is very hard to draw on this tablet. But anyway, let's assume that this circle passes through A, B, and C, all of them. Okay. What the important thing which we want to use here is what is the radical axis of these two circles? So they are sitting at point A, correct? So the radical axis will be the common chord which passes through A, and the radical axis will also be perpendicular to OX. So the line through A and perpendicular to OX is the radical axis of, if I call them gamma 1 and gamma 2. Is that correct? And this is the line L which we were going to construct. So what I want to really show is that prove that R dash lies on this radical axis. Or in other words, I have to show that R dash has the same power with respect to both circles. So R dash power with respect to gamma 1 and R dash power with respect to gamma 2. If this is equal, then we are done. Okay. So what is the power of R dash with respect to the red circle? It is
R dash F into R dash E.
R dash F into R dash E. And what is the power of R dash with respect to other circle?
R dash B into R dash C.
So is there any reason why these two quantities will be equal?
Yes, sir.
Because there is a third circle, right? The circle which is the diameter, which has diameter BC. Okay, lots of colors in this diagram, but anyway, I think you can follow. So because of this yellow circle, Obviously r dash has the same power. I mean, basically what you're really seeing is r dash is the radical center of all these three circles. It is lying on each of the pairs of radical axis, because the radical axis of the yellow and the blue circle is line BC. The radical axis of the red and yellow circle is line EF, and the radical axis of the red and blue circle is this line L. So all these three lines are in fact concurrent at point R, which again a property we have studied before. I forgot to mention, by the way, that this is called the radical center. Whenever you have three circles for which you are taking the pairwise radical axis, we showed that they are concurrent, but that point of concurrence is called the radical center. Okay, just for your information. So are we done then? Are you able to follow the proof? Okay. So take a minute to note down what you want. Main couple of things that we used in this problem. First is inverting the problem. Maybe you could have done it without that also, but I felt that this is the cleanest approach. So first we constructed, instead of constructing R as the intersection of L and BC, we constructed this R dash. Okay, and we want to show that the R dash lies on L. Okay, then the next important thing was to recognize what that line L is. So for that, so these red circles, the red circle with diameter AH, this was not given to you as part of the question, but so this is where you have to fill in the missing pieces based on your intuition or experience. You can say that this is what is going to be useful. Okay, so the more you practice, the more you will be better at guessing these missing pieces of the diagram. See, if I draw this diagram and ask you the same question, everybody will get it. But that is the challenge for you to figure out what is the diagram you need to draw. Okay. Then this was only one half of the question. The second part is I could construct point S and T in a similar way. So what I want to show is that all of them are collinear. So right now I constructed point R starting with A. So you can say, I mean, now we know that the point R or R dash, it is the same point, is the point where the feet of the altitude, this EF meets the base BC. Correct? I could do the same thing for the other cases also. I'll try. Actually, the diagram may become complicated, but so to obtain point S, I could construct join the other 2 feet of altitudes. So this would be point S, and point T would be somewhere far up. So I cannot draw it, but basically or down somewhere. Okay. So these 3 point R, S, and T, they are going to be collinear. That is the claim. Okay. So let me just draw that diagram again. I think so. I mean, one important lesson which I should take is try to draw your triangles as acute as possible. If you make it more isosceles, you will see what was happening in this diagram. This line DE was very much like parallel to AB. So the diagram is very hard to draw. The more acute you make the diagram, the easier it is to do this construction. And there is a trick to do that also. So I mean, basically you can use the circumcircle as the reference. Okay, so if I draw the circumcircle, which is not needed in this question at all, but to make drawing my diagram easier, I'm trying this out. Okay, so the idea is basically I can control the distances of my sides from the center, and if the triangle is acute, obviously every side will have a different distance. So I deliberately take the other segment significantly closer this way. So now you see what I guaranteed is that all the 3 sides have different distances with respect to the center. That is why this is going to be acute. Okay. So this is how I could draw the diagram, and now I can do this. So I'll just erase my circle. In exam, you can probably draw the circumcircle with a light pencil because you don't want to refer to that all the time. Okay. So now in this diagram, if I construct my altitudes, still it is not very. What did I do wrong? Okay, I'll just deliberately take. There is one book 90 degrees, but for my diagram, I'm just going to take it that way. now these are my point D, E, and F. So I want to show that if I extend these segments and let them meet the opposite sides, okay, so this is my point R, this is S, and this is T. So they are looking roughly collinear even with this bad diagram. So R, S, and T are collinear. In future, we are going to do one more proof of this using Menelau's theorem. In case anybody who already knows Menelau's theorem, you might already have figured out how to do this. But if not, for others, we will do another proof of this. But even with what we have studied right now, okay, going back to the original question, can you see that R has, what is the power of R with respect to the 9-point circle and the circumcircle? It will have the same power because basically RF into these two properties, RF into RE equal to RB into RC. Because of that, do you see that R has the same power with respect to 9-point circle as well as the circumcircle? So if that is the case and there is nothing special about R, so if R has this property that R has equal power with respect to 9-point circle and circumcircle of ABC, obviously S and T will also have the same property. So in fact, the line RST is nothing but the radical axis of the two circles, the 9-point circle and the circumcircle of ABC. So obviously, if there is radical axis, they will be collinear. But so interesting thing that we have discovered here is that obviously any two circles will have a radical axis, but for these two special circles, the radical axis is nothing but the points where the feet of altitude meet the opposite side. So those RST are in fact the radical axis. Okay, and so this is what you always find all the old properties that you have, old configuration. You knew already a lot of properties about 9-point circle, orthogonality, or orthogonal configuration, and all those things. But to that, we are adding more and more dimensions. That this is another different, totally different property about that same configuration. And this will keep expanding every configuration that you have. I mean, even in the in circle, X circle case, you will find some application of the power of a point. Okay, so your knowledge keeps growing that way for every configuration also. Okay, any doubts in this? Okay, if not, then we'll go to the next question, question 5. Okay, so I think we don't have enough time to complete this sheet, but we will do question 5, 6, and 7 maybe. Anybody has already solved question 5? Can you raise your hand? Okay, 2 people. 2, 3. Okay, is there anybody who has solved the entire worksheet? Then I'll give something completely different. Jadip, you have solved the whole worksheet?
Sir, I can, but I could for two questions, 6 and 8.
6 and 8. Okay, okay. Okay, then you can try the others. I mean, basically, I want to make sure nobody is sitting idle. If somebody has finished everything, do let me know. Then I'll give you something else to try. Okay. So this is probably more computational problem, but again, the point is not just to do the calculation, but do them efficiently. So it is simply we want to find the power of each vertex with respect to the 9-point circle and add them. So the 9-point circle has so many points, 9 points to be precise. So which of them do we use to find the power so that the calculations become the most efficient? So let's say we want to find the power of point A with respect to the 9-point circle. So can we use these 2 points, the midpoint of the one of these sides and the fit of the altitude? Let's call it Q. I don't have a better name right now. We could call the fit of the altitudes, fit the midpoints PQR, the fit of the altitudes DEF, and the other ones XYZ. Okay, so into AQ, that will be the power of, I think the notation I've used is rho A. Okay. And so similarly, I can find rho B, rho C and add them. Okay, so it's just a matter of computing this quantity. Okay, and finally, everything has to be in the terms of the sides of the triangle ABC. Okay, so to find AQ is obviously B by 2. What is AE? So AE is you can use cosine of angle A. So this is AB into cos A, or alternatively, you know, the extended version of Pythagoras theorem. So when you write that theorem for side BC, so BC square equal to AB square plus AC square, and so in cosine rule term, it will be twice AB into AC into cos A. Okay, so in that again, if you see the AB cos A term is nothing but AE. Okay, so I can take everything to one side and I get the formula for AE. So what will AE be equal to? AB square plus AC square minus BC square upon 2 times AC. If I put it in symbols, C square plus B square minus A square upon 2B. Okay, in general, this is useful to know and memorize also, because the feet of the altitude to the vertex, this distance you may use lots of times. So what is AQ into AE? Because B in this part and this part, B will just cancel, right? So we'll just simply have C square plus B square minus A square by 4. So this was the rho A. And by symmetry, I mean by cyclicity, you will see that rho B, rho C will also be defined similarly. Only these terms will change. So here you'll have minus B square and here you'll have minus C square. And if you add all of them, basically the coefficient will turn out to be the constant for all the A square, B square, C square. So you get A square plus B square plus C square, whole thing 1 upon 4. Is that what you want? Yes. Okay. Yeah, I think that's all there was to this question. Just basic practice, nothing difficult. Okay, I hope everybody follows. Somebody has a very different solution. I don't expect, because there is not much freedom in this problem as such anyway. Okay, then question 6. Okay, how many solved question 6? So question 6 is a bit tricky one, so I will give you a bit extra time to try it. But just to get you started, what we really want to show here. So in all of these questions, even before you solve the question, getting the intuition is very important. Because in this kind of question where there are some fixed parts with some moving parts, so what is constant, what is not constant, all of those things are very important. Okay, so if this is my circle, and this is the fixed line. Okay. So there is a point P on this line which is varying. Okay, so P position may change, and I want to construct tangents from. And these are points A and B. So intersect AB again. This is point Q. Okay. I'm interested in the circle with diameter PQ. Okay. So here itself, intuitively, do you see that as P will change, as P moves in various positions, Q will also shift, because if P moves more above and to the right, Q will also shift. So P and Q are both moving, but while they are moving, my claim is they are all a part of a coaxial family. So first thing is, whenever you say coaxial family, there are two kinds of families we know. One is the intersecting kind, which has two fixed points. So all of them, all the circles pass through two fixed points, and a non-intersecting kind, which is like the Apollonius family. So which of the two you think will be this one? Will it
The
be
non-intersecting.
non-intersecting?
No, it'll be intersecting.
Why do you think that? Because from what I just showed you right now, if P moves little bit up, Q will also move up, right? So if this circle which I'm drawing, that will also shift slightly up, then the two circles will be intersecting each other, right? So if you get that idea intuitively, then it has to be intersecting family, correct?
Yes, sir.
Yes, sir.
Yeah, okay. So then, okay, so it's an intersecting family, which means if I find those two special points through which the circle always passes, then I'm done. Because then what I'm showing is that no matter which point P choose, P and Q I choose, that circle with diameter PQ always passes through those two special points. Okay. So naturally, given the symmetry of the diagram, where will those points lie? They have to lie somewhere on this line. Is that fair? So So those two special points, wherever they are going to lie on this line. So maybe, I mean, roughly I'm drawing them somewhere. Maybe they will be here and here. I don't know. Okay. So these 2 points, we can call them X and Y. Okay. So, and in fact, we will have, because the circle is with diameter PQ, which means that it is going to be equidistant from PQ. So in fact, these distances are going to be equal. If I call this point T, this XT equal to TY. Okay, so this whatever is distance Tx I have to find. So if I find this distance Tx such that point X always lies on the circle with diameter PQ, then I'm done. Okay, so this is, I'm trying to backtrack, like from what I want to show, I'm trying to come up with equivalent simpler thing to prove. Okay, we are not actually started proving anything, but we are just making the goal little bit either simpler or easier to understand. So that's what we are looking at here. Okay, so with this basic understanding, let us try the problem again. So I'll draw the diagram again on one side. Mainly, actually, I want to right now what has happened. All the lines are very bold, so it is very hard to, for geometry, I should probably use slightly smaller ink size. So again, if I construct, this is point Q. So in a question like this, the most important thing is, so you can call this principle invariants. When some things are changing, what are all the things that don't change? If I understand that very properly, then the problem is easy to solve. Okay. So let us try to find these so-called invariants in this diagram. And as we already noticed earlier, one of the lines of interest for us is this one. Okay. So the line perpendicular to O and the line L. Okay, so I'll call this point T, same as before. And so the midpoint of, if I join OP, right? This is a 90-degree angle. This is also 90-degree angle. So if I call this point K and this point something M. Okay. So if you think about this a little bit, you realize that M is also an invariant. If I change the position of point P, you will see that M doesn't change. Can you see that? Let us see how. So firstly, do you see a cyclic quadrilateral here? Correct. KPTM is cyclic. So what will the power of O be? OT into OM equal to
Okay.
OP into OK. Can I continue? What is this also equal to? Remember, PA, PB are tangents, right?
Yes, sir.
So what is this equal to?
OA square.
OA square, which is a constant. This is the radius of the given circle. And obviously OT is also constant because T is the fixed point. So if OT is constant, the product is constant, then you see therefore OM is also constant. So in other words, even if you change the point P, the point M is going to be remain fixed. So in fact, if you look at what is point K going to do, it is going to remain on this semicircle or other circle, because point P can go below also. Okay, circle with diameter OM, K will always remain on that circle. Do you see that?
Yes, sir.
Yeah, okay. Anyway, we don't need that fact for our proof, but something just to note. Again, this diagram is very rich with properties. What I am asking you to show is just one small part of it. You can easily spend hours on this and come up with a lot of other useful coincidences. But anyway, so M is constant. Now, that special point X that we wanted, right? X and Y. Okay. So I wish I had another color. Let me use orange. So this point X, maybe it will lie somewhere here. So firstly, you will also see the circle with diameter PQ passes through K. So it passes through K, and maybe it intersects. Let it intersect the circle or this blue line at point X and Y. Okay. So next you draw it. Okay. So we actually constructed the circle with diameter PQ. I was avoiding to do that actually, but anyway, let me do it. Sorry. Okay, and so this line is this orange circle is intersecting the blue line at X and Y. Okay, so what can we say about, and what we want to show is that X and Y position is fixed. Even if P changes, X and Y don't change. Now again, you see PXQ is a 90-degree triangle. So what is TP into TQ? You see it is equal to TX square.
So TX into TY.
Yeah, or rather it is equal to TX square as well as TY square, correct?
Yes.
Correct. And I want to, what I want to claim is that this is constant. So it is enough to show that this is constant, correct? So if I prove that TP into TQ is constant. So even if point P changes and obviously point Q changes, this product doesn't change, then I'm done. Is that correct?
Yes, sir.
Okay. So TP and TQ, I want to relate TP and TQ in some way. What do you see any opportunity to connect them based on the given information?
Complete Pythagoras theorem?
Sorry?
Complete Pythagoras theorem, CPT?
Sorry, your voice is very low.
CPT, complete Pythagoras theorem. Maybe.
CPT.
If you like find some XQP and then XP square is PTTQ.
Sorry, I'm not. I think you're on the right track, but I'm not able to hear properly. So, are you talking about some similar triangles?
Kind of.
Okay. At least maybe I gave you the solution. At least my approach is some similar triangles. So, can you spot which similar triangles can help us to find the ratio or the product TP into TQ? So, firstly, what are the various angles which are equal in the diagram? So, if I consider this angle, for example, KPQ, you see it is equal to, because of the cyclic quadrilateral, it is equal to this angle OMK.
Yes, sir.
Okay, so then which, and obviously this is a 90-degree. So which triangles can we consider?
Q and
So OTP and MTQ.
OTP and MTQ, correct? Or rather I should say QTM. Triangle OTP is similar to triangle QTM. Okay, and out of this I can see that I can extract TP into TQ by taking the right ratios. So here I can take OT upon QT equal to TP upon TM. So what does that give me? TP into TQ equal to OT into TM. And because we already established that M is constant, so everything on the right hand side is constant. Therefore, this is also constant. So therefore, even if point P changes, along with that point Q also changes, the product TP into TQ remains constant. And because of that, I mean, this equation is always true, that it's equal to TX, wherever that point X and Y intersect. So therefore, the X and Y are also going to be constant on this blue line. Okay. So in fact, the family is the coaxial family we are talking about is all the circles passing through X and Y.
Yes.
Okay. And as I said, there are lots of interesting properties in this diagram. With little more calculation, you'll see that in fact, so whenever we have one coaxial family, there is a dual family, right? Of the all the circle orthogonal to this family. So you will realize that the given circle, the blue circle, is part of that other family. So I mean, unfortunately, whenever I do this, the diagram gets completely difficult to follow. But so if I just draw two members of the orange family, you will see that this orange family is orthogonal to the blue circle, and the blue circle is in fact part of the other family. So you will have all the circles like this in the blue family. Out of that, this family, this is one representative, the circle which was given to us. And for this blue family, the dark blue line is the radical axis, and for the orange line, orange family, the light blue line is the radical axis. So you see, I mean, the everything that we did in the previous lecture is hidden in this diagram, but it is just cleverly disguised. That is all. Okay. So any doubts in this question? Because it was I would say, little bit more tricky than the previous one, because first thing you have to guess. I mean, again, you see, this part was very helpful. First, even before starting the proof, we figure out what we really want to prove. The what was asked to us was in a very complicated or in a disguised way, that orange is following coaxial family. That doesn't explain anything to us what we really need to prove. So we have to convert that cryptic statement that all the circles form coaxial family into something more concrete that we can actually prove with the given information. Simplification is a very important step. Okay. Then after that, uh, so if I list out the most important ideas, first is simplification of the given problem. Okay. So you always try to reduce the given problem into something equivalent but simpler to prove. Either you break it down into two smaller parts, or you show that some special case is enough to be proven. Then the whole result gets proven. Or lots of other tricks like that. Okay. Second, the important thing is to determine what are invariants. What things change, what things don't change. So the fact that point M doesn't change was a very important milestone. Okay. And that you can, if you draw the diagram a couple of times differently, you'll see that on geometry also, but through a simple calculation also we saw that. Okay. And after that it was just similarity. Sorry, somebody said anything? Okay. So it was question 6. Question 7 is actually very easy. So question 7 is homework for you. It is same like question 5. It was just simply one line solution, 1 or 2 line solution. Okay. So question 7 I will not discuss today. You can try it at home. If you really get stuck, you can ask on the WhatsApp group. Somebody will post a solution. Okay. Question 8. Yeah, question 8 is actually a very big result, because it is going to relate to a topic called pedal triangle or Simpson line, which I don't know if you already studied it before, but question 8 is a big result. And unfortunately, I mean, the solution which I know for question 8 involves some construction which are not very easy to intuit. That how are you supposed to land up with this idea? I don't have a very good answer to that. I mean, from the looking at the solution, we can back calculate it. Okay, we can figure out that okay, these are the tricks involved. But directly, I don't know. Like if I give you time, if you solve question 8 on your own, that will be amazing. But in general, it is quite hard. So I'm trying to think what, and we also have only half an hour. This will definitely take more than half an hour. Question 8. Okay, let's do this. We'll do question 8 next time. Okay, because I want to spend a good amount of time introducing the notation, setting up all the things like that. So we will reserve enough time for question 8. We can move on to question 9 today. Okay. So you see, this is actually a shortlist problem. So IMO, the way problems are chosen for International Maths Olympiad, first all the countries propose their problems. So every country will submit a few problems. That creates what is called a long list for IMO. Then out of the long list, I think a committee or there is a voting jury which selects a short list first. So short list are typically like 30 problems, 7 or 8 problems of every topic: algebra, geometry, number theory, combinatorics, and they are arranged in increasing order of difficulty. So here what I'm showing is G1. So the problems for a geometry go from G1, G2 up to G7 or G8. Okay, so the higher ones are more difficult. Typically G7 and G8 is so tough that they may not even ask that in IMO. But G1, G2 are the simplest ones. So if you ask me, roughly the difficulty level of G1 and G2 could be compared to INMO. Okay, so if you at any point you want additional practice for INMO, you can solve this easy shortlist problems. So same for all the topics: G1, A1, N1, C1. So all the 4 subjects, you can do the first 1 or 2 shortlist problems for every year. So that will give a lot of practice material. Okay, so that's what even I'm doing right now. So we are solving 2013 question G1, and TH means I probably it was proposed by Thailand. Okay. Anybody has already solved this question? Can you raise your hand? Okay, Jadika. Question 9. I should draw the whole diagram. Sorry. Okay, so W is an arbitrary point on this side, and we are interested in the circumcircle of PWN and CWM. It roughly will look to be okay. And the diametrically opposite point of W on both of these circles. So if W in the centers, and H is of course the orthocenter. So I want to show X, H, Y are collinear. Okay. Let us see what we can do. So several pieces of information we have to use one at a time. So if we start with the fact that X and W are diametrically opposite, which means that any angle subtended by chord XW is a 90-degree angle. For example, this is a 90-degree angle, correct? But also, if you look at clearly, the two red circles which I've highlighted, they are intersecting at one more point. Okay, so if I call that point T, then you see XTW is also 90 degrees.
Yes.
And similarly, what is YTW? Also 90 degrees.
Yes, sir.
So then, how are XTY already?
So collinear. So you have to prove it.
XTY is already collinear. So I want to show that H also lies on that same line. Okay, so what I want to prove is H also lies on this XTY line. Okay. So for the two red circles, TW is the radical axis, correct? Is the radical axis of the two circles. So if I call the circle, is there some name already too? Okay, they're called omega 1 omega 2. is omega 1. So TW is the radical axis of these two. But do you see A will also be on the radical axis, because what is happening with A? What is the power of A with respect to omega 1, which is AN into AB, and power of A with respect to omega 2 is AM into AC. And are these two quantities equal? Because what are B and M and C? There is a circle passing through those.
Yes, sir.
Yeah, I mean, this is again the orthocircle or orthogonal configuration, right? So the feet of the altitude. So B and MC is a circle. So these are equal. So therefore, A has also same power with respect to both the two gamma 1 and gamma 2. So where should A lie?
So on radical axis.
Correct. So A lies on the radical axis, which is TW. So basically, A TW are collinear, and which roughly seems to be the case from our diagram also. Okay. So this is something which can be useful. But finally, we want to go to point H. So because of this, what we have is 80 into AW. So this can't be seen. 80 into AW is equal to AN into AB. Okay. And now here again, you need to use the information about orthogonal configuration. So if I draw line AH, okay, let it meet the opposite side in point L. Then what is AN into AB also equal to AH into AL, because there is one more cyclic quadrilateral. B and HL is cyclic,
Yes, sir.
correct? B and HL is cyclic. So again, I can use the power of A with respect to that. So 80 into AW equal to AH into AL. So you know that power of a point has a converse also. That if this is true, what can I say about the points H, T, W,
So
and
they are
L?
concyclic.
Correct. So therefore, T, W, H, L, they have to be concyclic. And if that is concyclic, then what is angle? Basically, do you see what is happening? Because this angle is 90 degrees, which means that HW was the diameter of the circle HLW anyway. And T also lies on that same one. So basically, angle HTW will also be 90 degrees. Then if this is true and this is also true, then you see with all of this together, basically X, Y, and H, they are all subtending a 90-degree angle at point T. Therefore, H also has to lie on the line XY. Okay. Again, I just quickly repeat all these steps. I mean, the more important thing for you to learn from all these problems you are doing is the motivation, that why you should think of a particular approach and not a different approach. So in this case, I mean, why you have to use radical axis? Because we have circles which are intersecting. So you have a common chord between the two circles, W and T. And those circles are also passing through points B and MC, which we already know are special points. They are the fit of the altitudes, and there is a circle passing through them. So again, you see A is the radical center of three circles, the two red circles and B and MC, the circle with diameter BC. Okay. So that was the first thing that we established, that A is the radical center of these three. And then using the power of A with respect to another set of circles. So the other circle BNHL, which is also part of our standard configuration. Again, I'm not drawing it because the diagram is going to complicate it, but this is something we all know, that the circle with diameter HB basically. So therefore, from that we got the power of A with respect to this AH into AL, basically this quantity we got. Okay, and then finally putting everything together, the converse of the power of a point. So all the building blocks of a solution, you know, but you still have to figure out how to put them together. Okay, and I mean you'll start to learn this with more practice. So don't get worried if like you are not getting through these ideas. Even if you get half the solution, see, even if you reach the point that okay, you found the radical axis part, okay, then you have made progress. So and if you write something like that in the exam also, you will get partial marks in RMO, INMO, etc. Okay, so your progress will be slow but steady. So keep trying at it. But important thing is after the problem is done, spend the time to understand the learning value. That what are the important ideas I applied here, and how I can apply those ideas in a different problem also. Okay. So with that, I think we have only 10 minutes left. So question 8 and 10 we will do next time. I have remind me to talk about one important point which we all need to learn, which is writing the solution properly in the exam. Okay, this point I mentioned on WhatsApp group because I mean we were coordinating the papers for this year's IMO team. So you may already know the result that we have one gold, one silver, and few bronze medals. But the important learning value for us while checking the paper is that students can learn to write the solution better. And this is not just for the reason of presentation, but that could also have technical value, because sometimes if somebody writes something which is not clear, which is not really the examiner cannot read it properly, then there will be ambiguity that is the student really understood what is written or not. So I mean clarity of writing on two levels. One is of course it has to be legible, but on another point it has to be well designed. So the construction of the solution has to be such that anybody can follow it easily. Like you may have read some very good textbooks which are so nicely designed that, or nicely laid out, that you have very little difficulty following one point after the other point. Okay, so you need to practice this writing habit. And as much as you may want to suddenly wake up one day on the exam and write all solutions nicely, you cannot do that unless you have practiced it before. Okay, so I mean take it as a very important thing to start doing from now itself, that you only if you start practicing the writing solutions right now, then slowly you will make improvements, you will fix your problems, like whatever mistakes, typical mistakes that you are doing while writing, you will learn to plan your solution better. So all of those things will happen, but only if you start practicing right from now. And so to encourage for us, all of us, to do that, what I'm asking you to do is as part of homework. So question 6 and 9, let's say, I mean I could choose any two questions, but I'm just looking at this, I'm particularly choosing a question which may be a bit more tricky to represent properly. So that's why I would like you to try and write question 6 and 9 properly on a paper and post that photo on WhatsApp. Okay, you can post it on the group itself. Okay, so that way I'll go through everybody's solution, and I will next time I will walk us through what are the typical mistakes that people may be making and where you can improve. And you know what, I'll also do the same thing. So what I showed you right now on the tablet, that is just a rough work. This is not what I'll write in the exam. So if I were to attempt question 6 and 9, I will also write out what will be my solution. And I mean even my approach may not be perfect, I may make some mistakes, but we will learn from each other's mistakes, and we will all learn to become better writers. Okay, that is very important. And maybe to be honest, geometry, this is not so much of a problem. Geometry generally things are logical, straightforward, and you have enough practice. You will face a lot of difficulty in combinatorics and sometimes in algebra 9 point number theory also, but particularly combinatorics. So that is where you need the maximum practice. So we will do that obviously when we come to the combinatorics topics, but let's start doing this anyway for now also. So I don't insist that you write down every problem you solve, because that will just spend too much time. Okay, there is no need to do that. But at least, I mean, out of 10 questions, even if you write 3-4 questions, that will give you enough practice and confidence to do it right in the exam. Then I mean, then in the exam you'll be confident that there also I'll write properly. Okay, you understand the difficulty, that you can't expect that if you're not practiced this beforehand, suddenly your presentation will be very good in the exam. That is very unrealistic, and unfortunately many students are in that disbelief that I will do anything I want while studying, and in the exam I'll write it properly. That doesn't happen from my experience. Okay, so take this as a homework. Question 6 and 9 which you already solved, write them properly and post it on WhatsApp for next time. Okay. Okay, with that, we have 5 minutes, so maybe the last thing to do is the puzzle. So I mean, last time's game. So I want to, after today I'll move away from mini games. There are many other things to do. Games are not the only way of trying out various puzzles. There are a lot of, you may have seen this like coin balancing puzzles also. Like there are like, 5 coins and one of them is counterfeit. So how many minimum balances you require to find out that fake coin? So there are puzzles like that. There are some logic based puzzles. So there's a lot of variety in that. So I don't want to restrict ourselves to only game theory. So, but just to complete this topic, let's say I'll finish on the last time's game, that coin, the gold coin game. Okay. So if you recall, the game was like this: that basically you have a one-dimensional chessboard or board which has some coins. So some normal coins, and there is one gold coin. Okay, somehow arranged on the board. And the in each move you can move the coins to the left or remove the leftmost coin. Okay, remove the left coin or shift one coin to the left by any number of places. Okay, and the winner is the one who takes the gold coin. And so as usual, what we want to come up with the define the winning strategy set and the losing strategy set. Okay, and we already found some examples. So for example, I think all of us agree that reaching this position is definitely a winning strategy, because if you reach this, now the other person has only one choice, which is to take the normal coin, and then you win. Conversely, obviously any position which has a gold coin with no normal coins before it, this is obviously losing position, because now here the other person can just take the gold coin. So not only obviously this is a losing position where the gold coin is in the leftmost square, but any position where there is a vacant square before the gold coin, that is also a losing position. Okay, so and I think you might have found a few other winning positions also, like CGC is a winning position, CGCC, CG followed by any n times C, consecutive C, so there should not be any gap. Or so all of this were like adjacent to the left edge of the board. Now let's go to position, like let's say there is one gap. Okay, so empty space followed by C and G. Can you tell me whether this position is winning or losing? And again, the definition of winning position is if you reach that position, which means that from that position the other person has to play and you are guaranteed to win, then that is a winning position.
So this is a
Position.
Winning position? Okay. Because basically to find out what are the possible positions you can reach from here. So there is only two possibilities, right? One is that he will move the coin to the left,
or we can remove it.
or we can remove, and both of them are losing positions. So again, on this side I should have written this position also. So you see CGC followed by any number of spaces and G is a losing position. Sorry, no, I don't think that is true. Sorry. This is losing because, yeah, correct. If a person faces this position, yeah, correct. This is losing position, correct. So yeah, correct. I was right. Actually, all of these are losing positions. Any number of spaces in between losing position. So CG is definitely a winning position. Okay, so I can put it in this side of the thing. Okay. So I want to basically outline the algorithm, that how do you find out all the positions. So one of the important properties that game theory guarantees that it is never possible to go from one W to another W. Okay, this is never possible. Okay, so which means that once I find a position in W, I can backtrack all the positions which can reach from here. Okay, so basically what are all the positions from where in one move I can reach CG. So for example, C followed by any number of spaces and G, correct? If I can reach from here to here in one move and this is in W, then this cannot be in W. This has to go in the losing position category. Okay, so that is how we have discovered a whole family of losing positions. Okay, So proceeding like this, let us solve the 2 coin case completely. So basically 1 normal coin and 1 gold coin. All the possible permutations of this case we will solve first. Then from there we'll go to the 3 coin case where we have maybe 2 simple coins and 1 gold coin. There also there will be cases like, for example, it could be like this or like this. So each of them will have a different strategy and different family to evaluate. So in general, this tree can get very complicated. I don't know if, I mean, the ultimate question we want to solve is, if I give any random position, like anyhow the CG are arranged, can you tell me whether this is a winning or losing position? That may be a very hard problem. I mean, at least I don't know a solution to that. But see if you can explore and come up with some nice trick to find out the answer to this question. Okay. Anyway, so I mean, in this process, we have outlined some ideas of NIM game, and we will revisit another very well-known NIM game later on, but not right now. I want to maybe divert from this and try some other puzzles next time. Okay. Yeah, I think that's all for today. Thank you. Bye.
Thank you, sir.
Bye.
Thank you.
Bye and thank you, sir.
Bye, sir.
Thank you. Bye.